In this video, I'm going to talk about how to conduct a MANOVA in SPSS, as well as show you how to check a few assumptions that are assumptions that would be in addition to ANOVA. All right, so first I just want to acquaint you a little bit with the data and tell you what question we're going to be examining today. So I'm using data from the 2012 PISA assessment, and I'm just pulling in a subset of the data here. Um, you can see that two of the things that we're going to use here, PV1 MACC, which is the algebra subscore, and PV1 MACS, which is the geometry subscore. And so we're only going to focus on two groups in this video to keep this a little bit more simple. So we're going to be looking at how students score differently based on gender, which is the female variable, where a 1 indicates female, 0 indicates male. If they score differently on these algebra and geometry subscores. So one of the first things that we might do is just to look at normality. So if you go to Descriptive Statistics, Explore, you can look at both of these together. And if you put female in the factor list, and it needs to be nominal, 3 little dots here, so it's categorical variable, then it will show you the break this out by whether someone is male or female, so you can see the groups separately. So under plots, I always like to turn off this stem and leaf plot. I don't know why they put that on there. I don't know who would want to see that if they're working with much of a big data set. So look at the histogram there. There are also some different statistics you can check here. I'm going to check the one that says Outliers just to get a good look at that. And then make sure to display both statistics. Click OK. And give it a minute to run, and then we can look at what these two different groups look like. So first, it might be helpful to notice males and females, how they're split based on how many, what the sample sizes look like for each group. They're actually pretty similar to one another. For both sets, 2,525 students that are male, and 453 female students. So I'm not expecting any issues because of the, they look pretty balanced. If we look at descriptives here, we see the mean for males for the algebra subscore at 492. Skewness and kurtosis are within bounds. They're within plus or minus 2. Standard deviation of 96 points. For females, slightly lower mean of 484, slightly lower standard deviation. Skewness and kurtosis look like bounds. And for geometry, we see similar things. So males score 470, females at 459. A little bit different standard deviations. So it's higher for males, lower for females. And skewness and kurtosis values look with bounds. Here's the extreme values. You can see that there are a few at the end here, just showing us the highest 5. So we may have some issues with some of these. And we'll be able to tell a little bit more by looking at the load here. So this is the histogram. It says female equals 0. So this is the males for algebra. Looks pretty symmetric. And like there's probably not much of it. For females, also looks pretty symmetric, but there may be an issue with kurtosis. Looks a little bit like there's more peakedness than would be true for a normal histogram, especially with this bar sticking up like that. A little higher. And looking at the box plots can also help us make some judgments about whether we might find differences. It also helps us point out outliers. So if we look here, see there's quite a few on the ends on higher end of the scale for scores. And females are have a little bit smaller range if we ignore the outlier. So there's more of a range of the outliers. Um, this may be something that's problematic because it could make differences whenever we look at homogeneity of variances or homogeneity of covariances, especially for the covariance, because we'd be looking at the two. Looking at geometry, similar thing, might have a slight skew to the right, but it's terrible. And here maybe also a slight skew to the right for. And if we look at the side-by-side box plots, it actually looks more similar than the algebra scores, but still a few more outliers out here, spread a little bit farther out. Could be another potential problematic thing. So that's all we can see from there. Something else that we need to do, though, is also check for whether there's a linear relationship between the two dependent variables, in this case, the algebra and geometry subscores. So one thing we could do is just look at the correlation. So if we go to correlation, bivariate, and put both of these things in here, and let's take a look and see what correlation looks like. So this could be problematic. Pretty high correlation of 0.885. Depending on what literature you look at, some places say a cutoff of 0.8. Some places say a cutoff of 0.9 will indicate 0.9 or higher, or 0.8 or higher would indicate multicollinearity. So there could be some multicollinearity here. And we expect these things to be fairly similar to one another. They're both math domains, and they are domains that are typically taught together in the same class up through 8th grade usually. And these are 15-year-olds, so about 8th or 9th grade students. We can also create a scatter plot. So if you go to Legacy Dialogues and scatter /dot, pick a simple scatter, click define, and we will put, we can put MACC, the algebra, on the y-axis, x-axis. It doesn't really matter. We're just looking for whether or not there appears to be a linear relationship between. Okay. And it appears to be linear. And something else that we can look at, if you double click on this, opens up chart editor. And there is this little symbol. You hover over it, it says add fit line at total. This will put a linear regression line through the data and give you some indication of the relationship. So this could be helpful to look at if you click on that and give a second to load it. And then on the properties box, it will ask you, what do you want? We want linear. So just click close here. You can see it on the screen here. It will also pop up as soon as you close this. You don't need to save anything. But you can see 0.87 is the slope. So it's definitely bigger than 0. R squared is up in the right-hand corner, R squared of 0.78. So seems to be a good linear relationship there. Updates the plot. Something else that you could also do is to run a linear model, just so that you can look at the residuals and confirm that the residuals are normally distributed. And it can also give you a look at that QQ plot and for the residuals to see if they are normally distributed, which also helps you make sense of whether or not a normal model is appropriate. But just from looking at this, I would say it looks pretty appropriate. I wouldn't anticipate issues. And so at this point, the rest of the things that you need to look at in order to assess whether this is the assumptions are met here will come from actually running the MANOVA. So if you go to Analyze, General Linear Model, and Multivariate, we want to put the dependent variables as these two different outcome measures. Female is the fixed factor, which only has two groups. If you click on plots, you can create some plots if you want to. I think we don't really need that here because there's only two groups. If there was more than two, it might make more sense to look at some plots, which we'll do in a different video. We don't need to run any post hoc analyses either because these are pairwise comparisons, but there's only two groups anyway. So there's not multiple groups that need to be paired together to compare with one another after running a multivariate level. So this can be saved for another video. And so at this point, we can leave it like this, except that we want to check some things under options. So we can go ahead and look at descriptive stats again. It just puts a small table at the top that's helpful. Estimates of effect size. So this will give us partial eta squared, which is interpreted like multiple r squared in linear regression. And then we want to see the homogeneity tests. And we can grab residual plots that show us things at the multi level for those dependent variables. All right. So click continue. Okay. Here's our descriptive statistics. If we just look down the standard deviation, looks like there could be some issues with Levine's test. Here's Box's test of equality of covariances. And we see that there is almost a statistically significant result here, 0.054. So because it hasn't gone below that threshold of 0.05, we would say there doesn't appear to be issues. The covariances seem to be similar enough, say that they're equal. Looking at the multivariate level, we're looking at the female row. We're not considering an intercept here. Wilks lambda is the most used version of this. So if you scroll over, you'll see the significance here is less than 0.01. The Wilks lambda value of 0.7, and partial eta squared is 0.003, indicating that 0.3% of the variability in the two outcome measures, algebra and geometry, can be explained by group membership. In other words, whether someone is male or female. So not very much of the variability is being, even though it's statistically significant, which, because the sample size is so large, that could be having an impact on that significance. Then we also see Levine's test of equality of error variances. This is done at the univariate level. So if we just look for the first one for algebra based on the mean, we see a statistically significant result, meaning that males and females have different variances that appear to be different enough that they're statistically significant. So it's not just based on random differences. This wouldn't happen by chance. And the same thing for geometry. Is also less than 0.05. So we have some issues with homogeneity of variances at the variate level. Could be having an impact on the results we're seeing. So at the top level, if we're assuming that things are okay, which they're not, so we need to recognize some problematic things that could be issues, then because we see a statistically significant result at the multivariate level, the next step is to examine univariate level differences. So looking at the univariate level Anova results. So here, if you look across the female line, you have algebra and geometry on separate lines. So it ran two different Anovas. And we see both of those are statistically significant. However, because we're running multiple, we'll probably want to do a Bonferroni correction. So we're looking for values Instead of 0.05, we would divide that by 2, so we're looking at 0.025. So this one is right there on the cutoff. We don't know how it got rounded up. Partial eta squared for both of those is still very small. A little bit more impact on the geometry test in explaining difference, but not much more to. So looking at the standardized residual plots, if we load here, because these are ones and zeros, well, the grouping variable here, we only see 2. But basically what we're looking at is the observed versus the expected should be a straight line. So we don't care about the predicted versus. Looks like a straight line there, around of 1, 5-degree angle. The same thing for the next one. So it looks pretty good. And doesn't seem to be a problem there. So that's further indication that a linear model is appropriate to dependent variables. And so that is how to run a MANOVA, and looking at a few of the key assumptions for running a MANOVA in SPS.